All right, Phasic students, let me try another video solution. I got a question on number 9. Let's give it a try here. We have a 50-meter length coaxial cable with an inner conductor that has a diameter of 2.58 millimeters and carries a charge of 8.10 microcoulombs. So I'm going to kind of draw a coaxial cable. Here's maybe the inner cable, and around it is this shielding wire. Then I'll give it a little bit of thickness, and so we'll just kind of imagine cutting it, maybe with the center wire sticking out a little much. And so here's the inner wall coming down. It says here the surrounding conductor has an inter diameter. Okay, so right here, the inner diameter of 7.27 millimeters. And then let's see, what was this diameter up here? 2.58 millimeters. Okay, so there's our dimensions, and let me just call this inner radius of the outer conductor B, and then the radius of the inner conductor I'll call A, because I think that's the same pattern definition that your author used in the textbook here. It says, what is the capacitance? All right, well, that's what this chapter is on, is capacitance. So capacitance is the amount of charge per volt. And of course, then what makes some of these problems a little more challenging is then you have to get the voltage. And so for the voltage, why don't I just integrate the electric field? And so I'll go from one to the other. Now maybe I'll draw a little picture of the electric field. They do say that on this inner conductor here is a plus 8.1 microcoulombs. So they're trying to say that the inner conductor is positive, making the outer conductor negative. So the electric field would be pointing outward. And maybe we should prove it's radially outward, because that's the next step in this process, is we've got to go back to another chapter. So this is 26, this goes back to 25, and this goes back to 24, where we apply Gauss's law in order to figure out the value of the electric field. And when we do that, you will see that it is radial outward and a cylindrical radial component, not a spherical radial component. And that'll give us the electric field. We'll integrate that. We'll get the voltage. Now, even though I made a distinction about which direction the field is, I probably should emphasize that the capacitance then is really the magnitude of the charge divided by the magnitude of the voltage. So we could integrate from A to B or B to A. That really would be the same number but opposite in sign. So I won't pay much attention to whether this integral comes out positive or negative. Maybe I'll just do it in such a way that it is positive, or just drop a negative. I'll probably just go from inner to outer, so that'd be a decrease in potential. So that'll come out to be negative, and then I'll just drop the negative. Yeah. Anyways, so let's start here with Gauss's law. If you remember, we did things like this. Maybe I'll just do the inner conductor here for a second and draw a Gaussian surface around it. And this is the surface around it. We argued that if it's a really long wire, every horizontal line could be a line of symmetry. In fact, looking down the top of it, Every line that goes across the center of the conductor would also be a line of symmetry. So from that, we know that the electric field is radially outward in a cylindrical component. We know it's the same everywhere up and down. The reason that's important is because when you go to do this integral, I guess since it's a closed surface, you might say that there is, and I'll cross that out, there is an area 1 plus an area 2 plus an area 3. And those three areas, maybe I'll kind of illustrate with a little sticky note here. But if I say, okay, this is going to be my Gaussian surface here. Okay. And I'm going to put my Gaussian surface around a conducting rod. So the pin will be my conducting rod, and I put a Gaussian surface around it. The Gaussian surface has a length of L, okay, and it has a top and a bottom. And so if we call this up here the top, and this down here the bottom, and then this the face of it, we are actually doing a closed integral. We've got the top and the bottom. Of course, remember, we're doing a dot product. And the dot product is the angle between the electric field and the area vector. So when we're doing Gauss's law for the top and the bottom faces here, or top of the cylinder and the bottom, with the electric field going radially outward, but the normal vector going up, this right here would have a cosine of 90 degrees, and same argument for the bottom one would have a cosine of 90 degrees. And so that's going to be 0, and that's going to be 0. In fact, visually, hopefully you see there's no lines of flux that would come out the top or the bottom. The lines of flux go, let me put my radial back in there and get kind of a pointing device here about, we'll use this little wood screw here, or actually it's a drywall screw, and I'll just say, look, it would be pointing, you know, in this direction all the way around, and nothing then would be pointing out of its top or out of its bottom, and so that's why we get 0 flux for them. Whereas we go around the face, the field is always pointing straight out all the way around. And that's in the same direction as the area vector. So this would have in it a cosine of 0 degrees. So as we kind of review all the way back to, I guess this is chapter 24 and Gauss's law, we can see that this would be just an E times an A, because cosine of 0 is 1 and these other two are 0. Okay, so maybe I'll put a page 1 here and say, all right, let's keep going with this. But as I go integral of E times A, this is the other part of the symmetry argument, besides knowing where lines of symmetry are so that we know what direction the electric field is. We could then say, okay, the electric field would have the same strength everywhere on what we call the face, because it looks the same from it. We couldn't make that argument on the top or the bottom, because if we moved somewhere on the top, we might get closer or further from it. So we could not pull this electric field out of the integral. However, it doesn't matter, because we already said it's cosine of 90 degrees, which is 0. But we can make that argument on the face of it, and so I'm going to pull the electric field out and then just have the dA. And so now this just becomes the area. Well, let me bring my Gaussian surface back here and maybe unroll it. And you can see then the area would be this I'll call it its width. We already called this the length of it. So here's the length L. And then this width of it is the curled up part. That's the circumference. That's the 2 pi r. So this closed Gaussian surface, which we divided into 3 surfaces, a top, a bottom, and a face. Top and bottom we got 0, and the face we said would be strength of the electric field on the face times the length of the Gaussian surface times 2 pi times r, the radius of the Gaussian surface. Now remember, Gauss's law said it's the charge inside divided by epsilon naught. So the charge inside of this thing, and so if this is the top and this is the bottom, it would be the charge along the interconductor of length L. Which, if we kind of think of this as the whole thing, we could also say that's the total charge. But we don't even have to really do that. We could just move then the L over to the other side of the equation and say we're talking about the charge enclosed. And if we make a surface that's not the whole length of the wire, it wouldn't be the full charge, which would be 8.1. It'd be some fraction of that. But it would be then spread out evenly, and so the charge over this length, whatever this length is, would be some value, which I'll call lambda. And so that charge per length would be the lambda. And there's the epsilon naught. And let me also move the 2 pi r to the other side. And so it's been a while since we've been in this chapter, but it was a nice review. And I say this chapter, I mean chapter 24. And so here is the electric field from this cylinder shape. Now, I'm not sure you have to go and actually do this integral for this problem, because I think your author is kind of implying that at this point you've already done it and you could just go back and maybe even have it memorized. But I think going back to chapter 24 and looking up the electric field from a cylinder is fine. So you could have started the problem right there. In fact, then if we take, as I said, this step and put it into here, we can go to chapter 25. So the change in the voltage would be the absolute value of this integral of the electric field over some line. And in this case, coming back to our picture, I'm going to go from this inner conductor, so the very surface of the inner conductor, to the inner radius of the outer conductor. So I'm just going to go along that green line. And so if I'm integrating along that, that means my dr is in the direction outward. And the electric field is outward. So technically the first step is to say this dot product, E dr, is cosine of 0 degrees. And of course, 0 degrees is just a 1. And so we've got the integral of this electric field, which we just did up here, 1 over 2 pi epsilon naught lambda over r dr. And then we would be integrating it from the inner radius, which I called A, to the outer radius B. And so this would be a 1 over 2 pi epsilon naught. Here's the lambda, and now the integral of dr over r is ln. And so I'll just take the b over the a. Now, I guess technically I'm still needing to take the absolute value of that, but let me just get rid of the absolute value signs and change that. Since b over a, b is greater than a, these would all be positive numbers. And so I have this little equation for the voltage difference, and I should say the absolute voltage difference, because if I had gone from the outer conductor in, the change in potential would be positive, and from the inner conductor out, it would be a negative. And so that's what I would have gotten if I didn't take the absolute value. But again, the definition of capacitance is a positive number. It's a positive charge over a positive voltage. So that's why we always call it a voltage difference. One way is positive, one way is negative, and everybody knows one way is positive and one way is negative, so you never talk about it. You just say the voltage difference is, and so you say, 7 volts. But so obviously there's a decrease this way of 7 volts, but an increase that way of 7 volts. Oh, and don't take that 7 volts too literally. I don't know what it is. I'm just saying that's what it should be. But I give that warning because it does say in part B what is the potential difference. So we're going to find it, and it's not 7. So I was just kind of making up a number here to show you that it could be, a negative this way of some number and then a positive of that way. So a negative 7 and a positive 7. We'll find out what it is when we get to part B here. But ultimately, we're trying to get to the capacitance. So finally, we can get to the equation for chapter 26. So I'll say it again. I had to do 24 with Gauss's law to get the electric field. Then I had to do 25 to do the integration of the electric field to get the voltage. And now finally, I'm actually doing the problem for this chapter. And I suppose you could have started right here because I think this was done in chapter 26. So maybe I should say that, even though I'm 16 minutes into this video, you could have started this problem right here if you either remembered it. But I think it's good to just kind of start from the fundamentals and not try to remember a bunch of stuff. All right, so then I have charge over the voltage difference, which I put a delta V, but if you're okay if I just put a V now. And I'll put the absolute value. All right, so if you come over here and you think about this capacitor, how much charge does it have? Well, they actually gave us a number, but I'm just going to put that as charge density times its length, because the voltage was this number here, 1 over 2 pi epsilon naught lambda over ln of B over A. So I can finish this calculation by saying the lambdas are going to cancel off, and they'll get the 2 pi epsilon naught up at top together with the length of the capacitor, and then the natural log of B over A. And so the capacitance has to do really with the geometry. What shape is it? How long is it? What are the two radii involved? It doesn't have anything to do with how much charge we put on or how great the voltage is, because these two are proportional. If you double the charge, you double the voltage. Or if you triple the charge, you triple the voltage. Or same the other way around. If you quadruple the voltage, you were going to have to quadruple how much charge. So those cancel off, and so the capacitance becomes all the geometric factors. The shape of it, the length of it, the radius of it. All right, so finally on here, I can now grab my calculator and calculate what this capacitance is. So it's 2 times pi times 8.85 times 10 to the negative 12 times, and I believe I read 50 meters. Yeah, 50 meter length coaxial cable. Divided by the natural log of the inner radius over the outer radius. Now, maybe just to make things a little easier on myself, I'll just double it, because now it would be the ratio of the outer diameter and the inner diameter, and that's how they gave it to me. And then also it's a ratio, so it doesn't matter which units I use. So I won't even bother to switch back here to the units. The outer diameter was 7.27, and the inner diameter, I believe, was 2.58. Let me check that one, yeah. And so together I come up with, looks like about a 2.68, and it looks like 10 to the minus 9, so nanofarads. And so there is answer to A. What is the capacitance? Now, continuing on then to B, let me continue to take advantage of this chapter, which again says capacitance is the amount of charge over the voltage, and rearrange it to say the voltage then is the charge over the capacitance, because they said the charge was 8.1 microcoulombs. And the capacitance I just did, 2.68 times 10 to the minus 9. And if you come back here, that's the nano. And the farad is a coulomb per volt. So the coulombs will cancel off, and we will be left with flipping and putting the voltage on top. So I would have this 8.1 times 10 to the negative 6 divided by the last answer, and I get just over 3,000 volts. Maybe with 3 significant figures, I'll call it 3,020 volts. All right, hope that was helpful.